So we've got G13, we've got rho C, and next we come to this equation here. Let's go rho C times S. Sorry, S is G13 L over D. So slenderness equals G13 L over D. And so our slenderness is going to equal 1.0 times L. L is 2,800 millimeters, divided by D, which is the major axis depth, 190. So S is 2,800 times 1 divided by 190, which is 14.7. S3 is 14.7, which, if you have a look here, it's 14.7 is midway between 10 and 20. So we're looking at the rho C. Rho C is just 0.96, so it's almost the same. Between 10 and 20, that's a transition column in the major axis. Okay. Now let's have a look at the minor axis. So S4 is the minor axis, and for the same reasons as before, we're going to take G13 as 1.0 because we can't be sure that it's got any end restraint on the ends of that column. So S equals G13 times L over B, the smaller dimension, and this time we got 1.0 times 2,800, and B is 35 millimeters because this was a 35 millimeter, 190 by 35 millimeter column. And when we go 2,800 divided by 35, we get 80. So S3 is 80, and rho C S3 equals 0.96 times 80 equals 76.8. So that rho CS is greater than 20, 76.8. You see it's actually a very slender column. So let's go ahead and work out K12, which is this formula here. So K12 equals 200 divided by rho C times S, all squared. And that equals 200 over 0.96 times S, which is 80, all squared. And that equals, we go 200.96 times 80, we'll square that, and divide by that, and we get 0.0339, or 0.034. What that's saying is, because of the slenderness of this column, the K12, we're only going to get about 3.4% of the potential capacity of this column compared to the crushing strength of the timber. So we have K12 now. Let's go ahead and work out the whole capacity of our column. So N DC equals phi. We know phi is 0.7 times K1. We know K1 is 1.0, K4 1.0, K6 1.0, K12 0.0339. We're using the smaller K12, and the smaller K12 is the one that governs between the strong and the weak axis. All it's saying is going to buckle in the minor axis before it buckles in the major axis. Times F-C. F-C is 18 megapascals. And finally the area is 6650. And if we multiply all that out, we get 0.07 times 1 times 1 times 1 times 0.0339 times 18 times 6650 equals 2848 newtons, which is 2.85 kilonewtons. That is the capacity of that member in compression, NDC. And if we come back to our original problem, we know the design force is 3 kilonewtons. N star equals 3 kilonewtons. So this column is a fail. It is not strong enough in its current form. Now, if we wanted to strengthen that, a couple of ways we could do that. If we managed to restrain this end for rotation about the weak axis, then that would raise this K12 factor enough to do it. If we said instead of 190, let's make that a bit deeper, that would have a marginal effect in that it would increase the AC value. But it wouldn't have any effect on the K12. However, if we increase that 35 to say 45, then that would radically change this. It would radically change this S value, and that would lift the K12 factor, and that would more than make up the difference. So if you face that, I would say let's use, instead of 35, let's use a 45 member, and that would do it. And that is how you design a timber compression member.